welcome to the podcast. This is Mr. White.
And Mr. Sadler.
And today we're going to do a little Isaac Newton talk. Actually, he was Sir Isaac Newton, right?
Oh, he's knighted?
I believe he was a knight. Sir Isaac Newton. And Newton, was, and this is not a word I use lightly, a genius. And so, we're going to throw a little picture of Newton up on the screen. And I know it's hard to believe, ladies, but Newton was single, but with all those good looks. Newton has a pretty interesting story that you could read about. We're not going to talk about the whole thing on the podcast here. But Newton is said to have done three things while he was still a student in college. I believe the year was 1666. The plague, or the Black Death, was making its last pass through Europe. And once you go to college, you'll understand this, but colleges tend to fester disease, and something like the plague would be a bad thing. So they sent everyone home. And if there's one place Newton didn't want to be, it was at home, because home was a farm, and he didn't particularly care for the chores that you would have to do on a farm in the 17th century.
Right.
Newton was a thinker. He was what we would call a theoretical physicist today. He didn't actually do the experiments. He thought about it. It made sense to him. He wrote it down. In 1666, it's said that he does these things. Thing one. He develops the laws of motion.
So the three laws that we're going to talk about.
The three laws we're going to talk about, plus the universal law of gravitation, which explains why the moon goes around the Earth around the sun, and how outer space works, basically. He verified Copernican theory and Kepler's work and Galileo's thoughts. That's pretty big. If he had just done that one thing, we would still be talking about Newton today. However, in order to do that, mathematically, he had to invent calculus. Now, this by itself is something that lots of people were working on. There was a German by the name of Leibniz who also invented calculus at almost exactly the same time as Newton, which we're going to talk about in just a moment. And he describes light as a wave. He was right. No one had even asked the question, what is light yet? But Newton knew enough, had enough understanding of the physical world around him, had made a few observations, and correctly describes rainbows and prisms and the color spectrum, and has it all make sense. It's absolutely unbelievable. I said it, but no one had asked the question, and he was answering the question.
Well, that's really where Einstein goes.
Yeah. And it's important that you bring up Einstein, because Einstein really was the next thinker. Newton did his work in 1660s, 1670s. Einstein comes along in the early 1900s.
Right.
So for over 300 years, there really wasn't any new or relevant thought in this area of physics.
It sort of shows you what he did.
Yeah, unbelievable.
To revolutionize physics.
We talk about calculus a little bit. The German mathematician Leibniz also discovers or invents calculus at about the same time. Newton didn't want to share credit for this. So this is what Newton does. He invites Leibniz to England so they can celebrate the victory of calculus together. He greets Leibniz, invites him to this meeting of great thinkers. Then he accuses Leibniz of plagiarism, and since he's a foreign national, not at home,
right,
he has him arrested and thrown in jail for the rest of his life.
Nice.
Newton was not a nice guy, but he was a genius. So he was certainly lacking in the people skills area. So just a little insight there. The focus of today really is going to be Newton's second law. We talked about the first law way back in section 1 earlier this week.
Right.
Way back. The second law is a little bit more mathematical, and you could get into some wordy definition, but as far as you're concerned...
one in the book that says the acceleration of an object is directly proportional to the unbalanced force acting on it and inversely proportional to the object's mass. But yeah, it's really just force equals mass times acceleration.
F equals ma. If you if you search on YouTube for an F equals ma Backstreet Boys parody, there are several. They're awful, but they do get the point across about force relating to any mass that is being accelerated. While it's painful to listen to, it does in fact get the point across. So what this is telling us, we see words like proportional and blah, blah, blah. Okay, we see that if you have a large mass, okay, and you try to apply the same force to a big object, you're going to have a tiny acceleration.
Correct.
Okay, or if you were to increase the force on an object without changing its mass, then the way it moves changes significantly.
Correct.
So remember, acceleration is a change in motion. And we've been talking about changes in motion since chapter 1, but without really talking about the cause.
Right. Talking about
Right.
forces.
So force causes acceleration. All right, that's important. And acceleration is a change in the motion. So the bigger the force, the bigger the change in the motion. This applies to both positive and negative accelerations. That's the basics of it. This is the mathematical part of Newton's work that we're going to study. And it's important that we see mass and acceleration are inversely related, and that we see force and acceleration are directly related.
Is this where we talk about the fly and the pickup truck or something like
We're
that?
going to save that one for Newton's third law.
Okay.
But yes, we will get to that discussion later when we get to the third law.
Right.
So sometimes you see terms like net force written down in your book, or balanced force, and it should be forces, or unbalanced forces. It's important that we define some situations for these.
Okay.
Let me help out. Net force and unbalanced force, these are the same. They're talking about the same thing. So the verbiage there is different, but it has the same meaning. Balanced forces, let's talk about those first. Balanced forces are boring. And this allows us to introduce the concept of a free body diagram. So what's a free body diagram?
It shows all the forces on an object,
So
basically.
it's a picture. And so let's say we have a table here. Okay. Let me go ahead and label that. You know it's art when it has to be labeled.
Right.
Right. And I have an object, let's say it's a book, sitting on the edge of the table.
Okay.
Okay? In order for the table to hold the book up, the table has to
Apply a force.
push up.
Right.
We're going to learn that's called a normal force. That'll
Right.
be another discussion. But the more obvious force is the book pushing down on the table
Right.
with the book's F sub g. What do we think that is? Force due to
Gravity.
which is
It's
the
weight.
object's weight.
Correct.
So any object with mass has weight. Mass and weight are different. We'll talk about that. But the force due to gravity is weight, pushing straight down. This is balanced. Balanced is boring. If you're thinking about architecture or civil engineering, you call this statics. Static meaning no motion,
Right.
not moving, balanced forces. You can do balance, say we have our car traveling down the road, looking a little bus-like. Okay? The car, okay, first of all, has some weight down. It's got some normal force pushing back up, the earth pushing back up. The engine is driving it forward, but we've got this huge restrictive force. What's that called?
Well, we've got air resistance, and we also have friction.
So air resistance is a kind of friction. We have all this friction. So it can be balanced if it's traveling at a constant speed.
Right.
Like when your car is in
Cruise control.
cruise control, right? So constant speed is balanced forces.
So a lot of times students like to think that constant speed is no forces.
But that's incorrect.
Right.
What's happening here, and that's a really good point to make, what's happening here is that we have all these forces so that the up and down force adds up to be
Zero.
and that the right-left force adds up to be
Zero.
0. This is why buildings don't fall down. Okay, I say it's boring, but it's actually very important.
Right.
This is why bridges don't collapse. This is why your car is able to have cruise control. It's not efficient for your car's engine, by the way, to constantly be accelerating. That's actually really hard on your gas mileage.
Right.
So this is the basic stuff. So you might see an equation that looks like this. And this is balanced forces. What's that squiggly sign I wrote out there in the middle?
Greek letter.
Greek letter. Sigma means
Is it total?
Total.
Yeah.
So the total forces equal 0.
So that's balanced forces.
That's balanced forces.
So if we add a force to that, we're going to make it speed up.
Right. So yeah, let's talk about that. So then we have the unbalanced situation. All right, so if I decide that I need to pass somebody, okay, I take the cruise control off and I hit the gas. So now I go back to my bus.
The engine is overcoming the frictional forces and
Right.
actually speeding up.
So my arrows here, F engine, would be bigger than the friction which is opposing the motion.
Correct.
Does the bus still have weight while this is going on?
Of course.
Yeah.
And the ground is pushing up on it exactly as before, the normal force.
Correct. And we'll talk about the consequences of this if, of the up-down part. But the right-to-left part means, so let me go back here. Some of the forces in the x direction are 0 because the right and the left balance each other.
Correct.
We could also write some of the forces in the y direction, the up-down. So the normal minus the gravity equals 0. So in this drawing, in the y direction, are they still balanced?
Yes.
Yes. If the normal force was bigger than gravity, it would have lift. It would take off.
Correct.
If the weight was bigger than the normal force, it would crush the ground beneath it.
Right.
Okay? So vertically, we're still balanced. But horizontally, the engine force is bigger than the friction force, so we write down the second law.
Right.
F equals ma. Right?
Right.
So mass is mass, but it would be talking about some horizontal acceleration.
Correct.
The same thing would be true if you hit the brake, okay, or tap the brake. At that point, the engine isn't working hard enough. Friction is winning. I use that term lightly, winning. And the bus would slow down
Right.
and have a negative acceleration.
Right. The negative acceleration is bigger, and therefore we're slowing down.
So, that's sort of the meat of this. Another part of the discussion, and I encourage you always to read the green pages in your book, is to realize that forces are vectors.
So that means they have a direction.
And that's why we use these arrows. Okay? Big right plus little left means in the end we're going to have
The net force is going to be positive.
to the right, right? So we're going to call this net force. Okay? Because right plus left is still right.
Correct.
We could do the other version, where here the net force would have to be to the
Left.
left, because left is bigger than right. You can have negative signs, you can draw directions, you can define this with angles. There's a lot of ways to do this. But the bottom line is we need to have some direction because force, in fact, is a vector. And I think the last thing that we want to talk about maybe is some possible forces that we could be adding to our diagrams. Okay? So the one we talked about today, didn't want that color, don't even know what color that is. The big one we talked about today was weight, because we all understand weight. We all have some sense of what weight is. We discussed this force of friction. What else did we talk about today?
Mass. We
well,
haven't yet.
Well, we haven't talked about mass,
Acceleration.
but if for mass to be, if it has mass, it has weight.
Right.
We talked about the normal force. And that's a little bit of a complex idea, but we'll get into that. And then we talked about the force of the engine. We talked about pushes and pulls. So sometimes we just define these things as FA. We call them applied forces. So we could be talking about a push, a pull, a rope, anything that isn't always present. It may or may not be there.
So like in the Investigate today, we pushed a cart with a ruler, so that would be the applied force.
That would be the applied force. And when we noticed some things, like if we quit pushing, it didn't get faster and faster anymore, right?
Right.
And if we didn't push at all, it didn't move at all, meaning that forces cause accelerations.
Correct.
I think we actually hit everything. There was a lot there in the green pages. I suggest you go back and read it, rewatch the pod, take some notes. So signing off, this is Mr. White.
And Mr. Sadler.